All right.
It's actually quite cheap. It's the cheapest ones I can afford on a regular basis.
Cheaper than Prodas is pretty cheap.
All right. So welcome back to Advanced Modeling Methods, and we're talking about boundary elements. We wrote our first code on our last class and compared those solutions to the exact solutions or the analytical series expansion solutions. From this point on, what we're going to do is kind of make that code a little bit more comprehensive. We are going to look into other types of elements because the elements that we defined, we formulated in class were linear in shape, constant in field value, right? So we had linear segments to define the boundary elements, and the temperature and the flux are defined as constant values within the element. Those are called linear subparametric elements. We're going to discuss other classes of elements today that can be incorporated or implemented in boundary element codes, and other pertinent things to actually writing a serious boundary element code, not just the MathCAD code, because as you can see that the MathCAD code that we wrote is a basic code that takes very simple geometries like a square or something like that. But if we want to write a general purpose boundary element code for at least heat conduction, we need to have a mechanism to actually write good interfaces, and also a mechanism through which we can actually implement good integration, because a high-level programming language doesn't allow you to do the integration the same way you can do it in MathCAD. The advantage is that you can program your own integration routine, control the error, and at the same time you can actually have solutions much faster than you don't have to wait for MathCAD or MATLAB to interpret the results. High-level programming languages like C, C++, and Fortran, a compile binary can actually produce results orders of magnitude faster than MATLAB or MathCAD. Okay, so first thing we're going to look at today is another type of element, the quadratic element, which is a little bit more flexible type of element because you can actually fit it better through geometry. So this is advanced modeling methods. And this will be lecture 13. Now consider quadratic subparametric boundary elements. Okay, we're still talking about 2D problems, and therefore the element is just a line. Okay, but now that line is allowed to curve. So now we have 3 points to define the line. Those are the nodes. This is delta gamma j, so this is element j, and this would be, if we're going in that direction, this will be x1, so let's assume that this is the domain, and this is the outside. This will be x1, y1 of element j, this will be x2, y2 of element j, and this will be x3, y3 of element j. 3 nodes. Now notice that the normal vector changes depending on the position within the element, so it's no longer a constant like in a linear segment. That normal vector, especially for the evaluation of the h term, the h influence coefficient, and actually changes as we position within the element, as we integrate along the element. So, and we have a field value node there, right at the center, coinciding with that particular node. So we have this segment is the geometric node, and this is a field node. This is basically for T and Q. Here we have same thing, eta equals -1, eta equals 0, and eta equal 1. So we're going to map a general geometry in space of a parabolic spline. So notice this is a parabolic spline because it's defined by 3 points, 3 geometric nodes. We're going to try to map a parabolic spline in space that goes from x1, y1, x2, y2, x3, y3. We're going to try to map it to 3 values of eta, -1, 0, and 1. Okay, so we are going to look for shape functions that can do that job. So, x of eta of element j will be x1 times n1 of eta plus x2 times n2 of eta plus x3 times n3 of eta. And y of eta for element j will be y1 y2 and y3. All right? And T of eta is just Tj, and Q is just Qj. Constant. All right? So there's a distinction in the way we model the geometry and the way we model the field variable. One is modeled as a parabolic, as a parabola. The other one is modeled as a constant. So n1, n2, and 3, no surprise, those are shape functions. Okay, but in this case now, these are parabolic shape functions. Actually, I think we defined them already when we're doing finite volumes. We defined the 1D parabolic shape functions. Right, such that n1 of eta, n2 of eta, and 3 of eta are the so-called quadratic shape functions. All right, and these are basis functions, remember? In order for them to satisfy these, they need to satisfy the basis condition. They need to be 0 at all nodes except at their own node where they become 1, right? So that x evaluated at -1 becomes x1, x evaluated at 0 becomes x2, and x evaluated at 1 becomes n3, all right? So these basis functions will be eta over 2 times eta minus 1 will be 1 minus eta, 1 plus eta, eta over 2, eta plus 1. Right? Note, these are basis functions such that n1 of -1 is equal to 1, and 1 of 0 is equal to 0, and 1 of 1 is equal to 0, etc., etc. Therefore, xj evaluated at -1 will become x1 of j, xj evaluated at 0, this is a -1, will become x2 of j, xj evaluated at 1 will become x3 of j. And same for y.
So you said n of 0 is equal to 0 and n of 1 is equal to 0, or is that theta?
Now n1 of minus 1 is equal to 1. When you evaluate this at minus 1, you get 1.
Okay.
Right? When you evaluate this at 0, you get 0. When you evaluate this at 1, you get 0.
Okay, you have a slash in 1 and not the rest, so I just wanted
Where's
to
the
make sure.
slash?
The n1 of 1 equals 0?
And 1 of 1 equals 0.
I was just confused because your other zeros don't have the slash.
Okay.
I just didn't know if I was.
Yeah, sometimes I forget. Yeah. And the 0 should be equal. So. Yeah, sorry.
That's cool.
All right. So what do we do with these? Now our elements are defined by completely different shape functions. And these shape functions basically look like this. And we've already drew them before. This is eta. Put the 0 here. 1. And minus 1. So this is 1. And obviously this is 1. And this is 1. So n1 goes like this. N1 of eta, as you can see, is 1 when evaluated at its own node. So this is first geometric node, second geometric node, third geometric node. The other one goes like this. Well, that's supposed to be a parabola. It's not supposed to be that square looking on the top. So this will be N2 of eta. And the other one is N3 of eta. All right. So let's go back to the boundary integral equation. That looks like C theta or xi d xi plus the integral over the domain, over the boundary of t of x h x is equal to integral over the boundary q of x g of x xi d xi. And now we can discretize it. So Ct is equal to the, or plus the summation from j equal 1 to the number of elements of an integral over delta gamma j of t of x, h of x of xi is equal to the summation from j equal 1 to n, the integral over delta gamma j of q of x, g x of xi d gamma. Now, since the temperature and the flux are both constant along each of the elements, okay, so because T and Q are constant on delta gamma j, we get Tj equal 1 to n Qj right? Now we need to do the coordinate transformation so that we can perform those integrals. Okay? The idea of doing the shape functions and parameterizing x and y with respect to eta is so that we can change the integral with respect to a general line in space to an integral of eta. So recall d gamma is equal to the Jacobian of the transformation times the eta, such that the Jacobian of the transformation is equal to dx d eta squared plus dy d eta squared. Okay, such that dx d eta is equal to x1 times n1 prime of eta plus x2 times n2 prime of eta plus x3 and 3 prime of eta, and dy d eta is equal to y1 and 1 prime of eta plus y2 and 2 prime of eta, y3 and 3 prime of eta. Okay. So we know what n1 is. Therefore, n1 prime is equal to what? Let's see, on the previous page. n1 is equal to n over 2 minus 1, or eta over 2 times eta minus 1. So that would be, this would be eta minus a half. The second one will be minus 2 eta. And the third one is equal to eta plus a half. So notice now that the Jacobian is a function of eta. Notice that the Jacobian is a function of eta and not a constant as in the linear elements. Alright? Also, recall that the integrand h of x and psi requires a calculation of the normal vectors. H of x and psi is equal to the gradient of g plotted into n, which is equal to dg dx times nx plus dg dy times ny. And the coordinates of the normal vector for these type of element are as follows. And x is equal to dy theta dy d eta divided by the square root of dx d eta square plus dy d eta square well ny is equal to minus dx d eta divided by the square root of dx d eta square plus dy d eta square. So notice that the denominator is the Jacobian. All right. So,
Quick question,
Mhm.
and I know you mentioned it before, but why is it negative in the ny dx data?
it's just because of the right-hand rule. It's just a cross product. The normal is a cross product of.
Of the,
So if you take the element,
it'll be flipped that way.
yeah, it's just so that the normal vector always points outside. If the element is defined in a counterclockwise direction, it has to be dy d eta minus dx d eta. If you
Otherwise-
want the normal pointing inside, this will be minus dy d
that would
eta
be
plus dx d eta.
Okay.
So this guarantees that the cross product of these normal vector times the tangential vector, which is the vector,
Give me the direction.
always gives you 0, because
Okay.
they have to be perpendicular.
Right.
The tangential vector is the vector that goes from x1 to x2 or from x2 to x3.
Mhm.
It's a line vector.
Mhm.
If you multiply that times the normal vector, you should get 0 because,
It's
well,
it's
the-
perpendicular.
I'm sorry, not the cross product, the dot product of two perpendicular vectors always gives you 0.
Mhm.
So if you multiply these times the tangential vector, you always get 0.
Okay, and it's because
And
of
the denominator is like this to guarantee that these are unit normal.
right.
That's unit in length.
Mhm.
Yeah. Alright. So basically, where do we end up with? If we go back to our discretized boundary integral equation, which is this one here. Well, basically we transform these integrals into just integrals over a parameter. So this would be simply C, so the discretized PIE becomes, so now we have C T plus the summation from j equal 1 to n of Tj times the integral between -1 and 1 of h, x, and xi times the Jacobian times the eta is equal to the summation from from j equal 1 to eta to n qj times the integral between minus 1 and 1 of g, x, and xi, the Jacobian dA. And those are the influence coefficients. So this one we call, so collocating psi at xi, yi, such that I goes from 1 to n. So we collocate the source of the direct delta function at each of the boundary nodes, but only at the field value nodes. Okay. So then we have C I T I plus a summation from j equal 1 to n Tj H Ij is equal to the summation from j equal 1 to n Qj Gij. Well, you can see what Gij is simply equal to the integral from minus 1 to 1 of g of x psi I, Jacobian eta, and this will be the Jacobian of element j, the eta, Hij with a hat, so same thing as before. The only difference is that the Jacobian now is the function of eta. Before, in the linear segment element, the Jacobian was just the length of the element. It was x3 minus x1 squared plus y3 minus x1 squared, square root of that, divided by 2. It was the length of the element divided by 2. That was the Jacobian of the transformation. Now the Jacobian actually is a function of the integrating variable. So then, this becomes Hij times Ti is equal to Gij times Qi, sorry, J, such that Hij is equal to Hij plus Ci times the Kronecker delta. But that's okay because we know we can calculate the diagonals of these by adding the off diagonals. Same thing. Note that the diagonals of the matrix H, that is HII, can still be calculated using the equipotential. Condition. That is, HII is equal to minus the sum from j equal 1 to n, where j is not equal to I of Hij. Alright, so we end up with exactly the same thing. A matrix that multiplies the temperatures, another matrix that multiplies the fluxes. We rearrange that depending on the boundary conditions, right? Some of the fluxes we keep on the right, some of the t's we send to the right. Everything that we don't know we put on the left, okay? Depending on the combination of boundary conditions in all our elements from 1 through n. The only difference is that within the calculation of each of these influence coefficients, there is a Jacobian now in the integral that's slightly different, not slightly, but considerably different than before. So that integral now is slightly different. Still an integral of eta, It's a 1D integral. So the mechanism through which we can do this doesn't change. Okay. Also, the element GII cannot be found exactly anymore, like before. GII must be found through numerical integration. It cannot be found analytically like we did before. We found the equation for it. It was the length of the element divided by 2 times 1 minus the log of the length of the element divided by 2. That's only for linear segments, not for quadratic segments. And this is my element of choice. Okay, this is what I like to employ. Elements are quadratic. That way I have a little bit more flexibility and liberty of modeling any type of geometry. Okay, if I have a curved geometry, I don't have to staircase it. Essentially, I don't have to actually use linear segments to model a curved geometry. I can use quadratic or parabolic spline, like these are, to model, and it would actually attach to it pretty nicely. And with a little bit of change to the code, just adding a Jacobian there, we get the right results. All right. Now, so far we haven't considered the possibility of allowing the temperature and the flux to change within the element, right? The two elements that we've identified, which are the linear subparametric and the quadratic subparametric, let the temperature and the heat flux be constant throughout the entire element. Okay, that's fine. Okay, at least for heat conduction problems, it's fine. When you go to elasticity problems, you may have a problem. Okay, but how can you mitigate that problem? Two ways. You can increase the resolution of the discretization, right? You can make the element smaller so that the length over which temperature and flux are constant is not that much. Okay, that's kind of the logical way of doing it. The other way to mitigate that is just, well, if I don't want to increase the resolution of the discretization, I want to keep the same number of elements, I can increase actually the size of, or the way I model the field variable T and Q within the element. I can actually use splines or shape functions to let the element or to let the variables change within the element. I can assume that the temperature and the heat flux change quadratically or linearly within the element and use shape functions as well. Those are the two types of mitigation that you can do. Those are in finite element language, that will be the P and H type of resolution. Okay, P will be increasing the way, the order of approximation of the field variable. So instead of using constant, we can use linear or quadratic. H will be increasing the resolution, so increasing the number of elements, making the elements smaller. So in finite element lingo, that's called P and H resolution. And boundary elements, it's just that. All right. So I'm going to jump to quadratic isoparametric. So notice we went from quadratic subparametric. The ones we explain are really subparametric because geometry is quadratic, field variable is constant. You can do geometry quadratic, field variable linear. You can do quadratic geometry and quadratic field variable. So consider quadratic continuous isoparametric boundary elements. In this case, again, let me draw it again. Here's an element. The element is defined by 3 nodes, and eta equals -1, eta equals 1, 0, eta equals 1. This is element delta gamma j. Let's assume that the domain is on this side, therefore the normal vector will point to the outside. And now we also have 3 field variable nodes. And they're called continuous because the field variable nodes coincide with the geometric nodes. These are called continuous elements because the field nodes, so these coincide with the geometric nodes. All right? So what we have is x of eta will be x1 and 1 plus x2 and 2 plus x3 and same thing for t. So we're going to have a t1, same shape function, t2, same shape function, and t3. Well, q, same thing, q1, q2, q3. All right? Such that n1, n2, and n3 are the same quadratic shape functions described before. So now what's the difference? In the discretized boundary integral equation, what do you think will be the difference? We'll have temperature times h's, we have q's times g's, we have a matrix of influence coefficient, and so on and so forth. Well, how many temperatures we have now? If n is the number of boundary elements, how many temperatures we have total? 2 times n, right? Even though we have three nodes per element, we have a total of 2 times the number of elements, total degrees of freedom, temperatures and fluxes, right? Because one node repeats with the same element. The final node of the first element is the first node of the second element, and so on and so forth. Okay? So, after discretization and collocation, the BIE becomes CI/TI plus the summation from j equal 1 to 2n of Tj times Hij equal to Qj times Gij, such that I goes also from 1 to 2n. Such that there are 2n degree of freedom, Tj, Qj, such that j equals 1 to 2n. So you just double the size of the system. Okay? So doubling the size of the system, or squaring it, because now the matrix is 2n by 2n, also means that you just basically delay the solution of these by a factor of 8, right? Because the solution of the system of equation is usually proportional to n cubed, number of floating point operations. Before you add n, now you have 2n, so you have 2 to the power of 3. It's going to be 8 times slower to solve this problem. That's not a big deal if you're talking about 1,000 elements, but in 3D, when you're talking about hundreds of thousands of elements, that's a big deal in terms of memory, and that's a big deal in terms of speed. Okay, you can wait hours to get an answer. So these increases memory demands by n squared, 2 squared, and computational time by 2 to the power of 3. Now, I particularly don't like continuous elements for 2 reasons. Bookkeeping becomes an issue because now you have to keep track of the last node of one element coinciding with the first node of the next element. You have to keep track of what the next element is or where it is. So you have to have some sort of connectivity. Remember where I used to tell you can just define one element here, another element there, another element there, and you have no problem. There's no reason why you have to have a sequence. We have a sequence because it's easier to build an interface when you have a sequence, right? But in this case, if you don't have a sequence, you have to have a connectivity, right? You have to say, well, element 1 is kind of connected to element 6, and element 6 connected to element 7, and so on and so forth. That's one issue, bookkeeping. So, continuous elements. Create bookkeeping issues because one must keep track of what elements share which nodes. Also, continuous elements create corner issues. And that one is the biggest issue. And what is a corner issue? Well, let's say that you're on a corner. Let's say that you are a 90-degree corner, for instance, and then you have an element here. So let's say that this is element delta gamma, I don't know, 20, and this will be element delta gamma 21. Okay? So this is this element. Okay, and this will be 1, 2, and 3 of that element, and this will be 1, 2, and 3 of element 21. Okay? So this will be, let's assume that this is the domain, so it's pointing this way. So if we go counterclockwise, this will be element 1, 2, and 3, or nodes 1, 2, and 3, and this will be nodes 1, 2, and 3. All right. So we solve the system of equations, right? And we get a temperature at this node. So is it okay that the temperature at this node has a single value? Right? Yes, it is. Temperature is supposed to be a continuous single value variable. Right? The temperature at this point should be the same, whether you see it from this element or whether you see it from this element. So doing this connectivity is fine. How about the flux? You're going to get a single value for the flux because you have 2n numbers of degrees of freedom. So you're going to get a flux here, you're going to get a flux here, you're going to get a flux here. So these two elements are going to share the flux at that point. Is the flux supposed to be the same? The normal flux, that is? It's not. The flux is not the same because one is dt dx and the other one is supposed to be dt dy. One is the gradient multiplied times the normal vector of this element which points in that direction, and the other one is the gradient multiplied times the normal vector which points in the y direction. So they're supposed to be two completely different values, independent of each other, right? So getting a single value is the wrong thing. So what do? Then you have to decompose it, apply some kind of magic, kind of hand wave a little bit, and say, well, that's the value, but not really. That would be the value if the normal vector were 45 degrees, sort of, right? But the normal vector is not 45 degrees. You have a singularity. So notice that Q23 and Q21 should not be the same. But, well, one is multiplying this normal vector, the other one should be multiplying this normal vector. But this system yields a single value of Q at that node. That's a corner issue, which is not good. And by the way, that's the same thing in finite elements. Finite elements, you have coordinate nodes. In coordinate nodes, you have single fluxes, or you have single tractions. Same things for the traction. Because retraction, remember, is a stress tensor times the normal vector. Traction is the same. In this case, the scalar is the temperature. The gradient of the scalar times the normal vector gives you the flux. In the case of elasticity, you have the deformation. The gradient of the deformation is a stress tensor, or a strain tensor, I'm sorry. That related to the Young's modulus and the Poisson ratio gives you the stress tensor. The stress tensor multiplied times the normal vector gives you the traction. When you solve this using finite elements or boundary elements at a corner, you get a single value for the traction. And if you have a corner like that, that's a problem. If you're talking about a flat surface, well, the third node of this element and the first node of the next element are supposed to have the same Q, right? But not when you have a discontinuity there in the geometry. So how do we do it? How do we solve this problem? So these two issues can be easily addressed using quadratic, discontinuous, isoparametric boundary elements. All right, well, for the subparametric ones, it's never an issue, right? Because the subparametric elements, the node is never at a corner. On the previous one, you have the segment, the node is always in the middle of the segment. Whether the segment is linear or quadratic, the node is always at the center. So there will never be a corner issue. But if you want to use high order elements, you still want to use high order approximation over the element, then you must you must use discontinuous elements. At least that's my belief. And all the codes that I've written, even used commercially or used at NASA or wherever they were used, use discontinuous elements. You don't have to worry about dull value, and you don't have to worry about mitigating corner issues applying magic. All right, so how are these elements? These go like this. So let's say this is the three geometric nodes. Again, this is delta gamma j. Let's say that the normal vector points like that. So here's the domain. All right, so this is eta equal -1. This is eta equal 0. And this is eta equal 1. And then you can place three nodes. One here, and one here. And you place these nodes at eta equals -0.75. This one at eta equals 0. And this one at eta equals 0.75. That's all you have to do. All right? So, xj of eta is equal to x1j and 1 eta plus x2j and 2 eta plus x3j and 3 eta by eta is equal to y1j and 1 eta plus y2j and 2 eta plus y3j and 3 eta. But the temperature, now you're going to say, is T1 J M1 eta plus T2 J M2 eta plus T3 J M3 eta. Same for the flux. Q1J M1 eta, Q2J M2 eta, Q3J M3 eta. So now you have different shape functions for the geometry and for the field variables. They're both quadratic. But notice that M1 must go to 1 at eta equals -0.75, and it must go to 0 at eta equals 0, and at eta equal plus 0.75. So the basis actually changes. And I'm not going to derive these for you, I'm going to just write them here. M1 of eta equals to 2/9 of eta 4 eta minus 3, and 2 of eta is equal to 1/9 of 3 minus 4 eta, 3 plus 4 eta, 3 is 2/9 of eta, 4 eta plus 3. Notice that they're quadratic, but they're anchored at different locations. All right. So notice this one, when eta is equal to -3/4, this one becomes 1. And when eta is equal to 0, this will become 0. And when eta is equal to +3/4, this one becomes 0. Okay? This one will be 0 at eta equals +3/4 and eta equal -3/4. And it will be 1 at eta equals 0. Right? So they satisfy basis properties. These are quadratic and satisfy basis properties at A dot equals minus 3/4, A dot equals 0, and A dot equals 3/4. Which, by the way, I found these to be, I derived these shape functions and found them to be kind of optimal to what I was doing, but you can place those nodes wherever you want. You can put them halfway here at 0.5 and minus 0.5, you can put them closer to the edges, whichever you want. They will just never touch the edge of the element, and therefore there will never be a corner issue. Okay? The only problem with these is now the size of your system has tripled. Right? Now you have 3 nodes per element, 3 independent nodes per element, so you have the system of equations going to be a size 3 times n. Okay? So you basically increase the memory demands by a factor of 9 and increase computational time by a factor of 27. Right? But you don't have corner issues, it's much more accurate. So let's write that down. So the collocated, discretized BIE becomes CI TI plus summation from j equal 1 to 3n of Tj Hij is equal to summation from j equal 1 to 3n Qj Gij such that I goes from 1 to 3n. So these elements increase memory demands by a factor of 3 to the power of 2, and computational time by a factor of 3 to the power of 3, that would be 27, with respect to constant elements. However, they are much more accurate and stable, and don't suffer from corner problems. All right. So I'm not going to go through the derivation of what the G's and the H's look like. You can figure that out on your own. However, we're not going to implement this in this class. Okay, I've written dozens of codes that I can actually put out for download. But what we're going to do, what we're going to do on Thursday, we still have another 10 minutes, I want to talk about something else, but what we're going to do on Thursday is basically we're going to implement all of these. But we're going to use the quadratic elements, the quadratic constant elements, the quadratic subparametric elements, and we're going to write a high-level program for these, high-level applications that you can use for whatever geometry you want, because project number 2 is going to include you analyzing non-square geometry with curves and things like that. Okay, and then I'll ask you to report some things like temperature. You can use other codes to actually test that what you're getting with the boundary element code that we're going to do in class is accurate. Okay, obviously the problem I'm going to give you for the project doesn't have an analytical solution because it's not in a square or rectangle. Okay, it has holes in it and things like that. All right, so whatever type of element you use, let me actually write this on another page. whatever type of element you decide to use, an integral of the form I, the integral from -1 to 1 of f of x dx will need to be approximated. When we wrote our MathCAD code, well, we let MathCAD do it for us. We gave it the coefficients. Each coefficient ij for any value, for every value of I, for every value of j, includes an integral from -1 to 1 with an integrand that's different. Sometimes it's g, sometimes it's h. There's a Jacobian in the middle, and so on. And we let MathCAD do it, and MathCAD didn't do it magically. It's not that MathCAD somebody symbolically integrating this. There is a numerical rule behind it, either a trapezoidal Romberg or adaptive integration rule that goes behind it. Now, the most efficient way of doing this is through quadratures. The most efficient and accurate way of performing these integration is by using Gaussian quadratures. So what's the idea behind Gaussian quadratures? You have the integral between -1 and 1 of f of x dx can be approximated by the summation from j equal 1 to m of some weights times the function evaluated at some specific locations, which are called the quadratures, between -1 and 1. That's simple enough, right? So all we need to do is find those locations between -1 and 1 and those weights between the 1 and 1, or the weights, I'm sorry, the corresponding weights, and take that function, which we know, evaluate it, multiply it times the weight, add them up, and we have an approximation of the integral. That's a quadrature rule. The good thing about quadrature rules is that the idea that Gauss had was, well, Taylor had said that you can take any function and expand it in terms of a polynomial, right? Any function you want. You can take a sine, a cosine, exponential, log, whatever, and you can expand it into an infinite polynomial series, right? So can we integrate a polynomial? Integrating a polynomial is super easy, right? Integrating other functions might not be easy, might not even be possible. So Gauss's idea was, okay, let's create rules so that we can integrate polynomials exactly. So I'm going to take a polynomial between -1 and 1. Let's say I'm going to take a 10th degree polynomial. And I'm going to integrate it exactly. I'm going to find the weights and I'm going to find the locations at which I have to evaluate that function so that the integral of that polynomial is exact. That's the basis behind Gaussian quadratures. Gaussian quadratures evaluate the integral of a polynomial of order 2m plus 1 exactly. Right? Does that make sense? Right? So the more m's you use, the better the approximation would be. Right? So you have 3-point rules, 5-point rules, 7-point rules, so on and so forth. And those evaluate, a 7-point rule will evaluate an order 15 polynomial exactly. But what good does it do to evaluate an order 15 polynomial exactly when my function is not a polynomial? I'm trying to integrate logs, or I'm trying to integrate 1 over r's. Those are what my functions look like. Well, I know that a log can be expanded as a polynomial. I know that a 1 over r can also be expanded as a polynomial. That's fine. So that approximation is good because the function can be approximated as a polynomial as well. All right? So these are called the weights, and these are called the quadrature points. So these integration or these approximation, let's say it that way, approximation integrates a polynomial of order 2m minus 1 exactly. That is a, let's say, 5-point rule integrates a ninth order polynomial. Exactly. Okay. Furthermore, and what's more important, and that's what we're going to use for numerical integration when we go to the computer, furthermore, the Gauss-Kronrod extensions not only are accurate as m increases, but also provide an error estimate which can be used a priori to set up adaptive rules. So what does that mean? Well, because the Gauss-Kronrod extension, which is basically use a pair of weights and a pair of quadratures. The idea is if you use a 5-point quadrature and a 7-point quadrature, the 7 is supposed to be more accurate than the 5, right? You compare the two results and that should give you something that is approximate and proportional to the order of the accuracy of the approximation. How about you do it in reverse? How about you use these and tell them, well, I want to solve this problem, solve this integral, but I want the integral to not be off the exact solution by more than 10 to the minus 6, right? You set your tolerance. Then you can use this in reverse, and then the subroutine can actually determine how many adaptations it needs to do, how many points it needs to use, and how many times it needs to break the integration line. It does that automatically. Okay, we don't have to worry about that because we're going to extract these from libraries that already exist. I'm not going to bother you with writing our own routine. So the Gauss-Kronrod rules can be found. These can be found in the popular pack libraries, and these are for C, C++, and Fortran. In the form of quags, single precision, or dequags for double precision. And obviously everything we're going to use in this class is going to be double precision because our matrices require that. So the error estimate can be used as a preset tolerance for the routine to automatically adapt. That means increase the number of quadrature points to satisfy set tolerance. Okay, so it's very powerful. And again, I'm going to bring up the routine. We're going to use it blindly, like a black box, but I'm going to bring it up, and you're going to see what the quadrature points are, what do they mean, and they always evaluate an integral between -1 and 1. Why only between -1 and 1? Well, because you can take any integral in the world and turn it into an integral between -1 and 1. You can just parameterize it. If I give you an integral between 3 and 10, you can just do a change of variables and turn it into an integral from -1 to 1. It just happens that Gauss and Legendre and Cronrod, the people who actually came up with these things, worked it out in general from using polynomials that have span between -1 and 1. That's it. All right, so this is it. So on Thursday, what we're gonna do is just, I actually already wrote the program. I used a stripped down version of some of the codes that I've written, just for heat conduction, steady state heat conduction, and homogeneous media with no generation. And what we're gonna do is go over these routines. You're gonna see how simple it is, and then how powerful it becomes, and then how fast you can get answers to. All right? Any questions? So I'll see you Thursday then.
Did you write the quad pack libraries?
No, that's part of QuadPack.
Okay.
QuadPack.
You said the popular. I didn't know if you were complimenting yourself.
Oh, no, that's part of. Yeah.
Genius quad